What's up, everybody? Welcome to this another video lecture in probability. In this video lecture, we're going to discuss about some family of discrete densities. Okay, so we start with the discrete uniform distribution. Okay, so imagine we have a finite set with n elements, say 1 to capital N. And then we're going to assign uniform probabilities over those n elements. Then the probability of each element in the set will be 1 over the total number of elements in the set. So in that case, that will be 1 over n. So if we have a random variable whose outcomes are those elements in the set and whose probability of each outcome is the number 1 over n, then that random variable follows the discrete uniform distribution. Okay, so in other words, if the random variable is x, then its probability mass function, which we denote by f sub x, and as a function of x, then its density is given by 1 over capital N times the indicator function that x takes on the values 1, 2, up to capital N. Okay, so it's right here. That's the density of a discrete uniform distribution. Okay, now in this video, we're going to be discussing the mean, the variance, and the moment generating function of the special distributions that we will be discussing here. So for the discrete uniform distribution, we have the expected value is just capital N plus 1 over 2. Its variance is capital N squared minus 1 over 12. And its moment generating function is 1 over n times the sum from 1 to capital N of e to the tx. Okay, but before we derive those I have just mentioned, let's have an example first of a random variable that follows a discrete uniform distribution. I know we're very familiar with this experiment, running a fair die. So there are actually 6 possible outcomes. And so our capital omega is the set containing 1, 2, 3, 4, 5, and 6. Now if the if the die is fair, then the outcomes 1, 2, 3, 4, 5, and 6 have equal chances of occurrence. So we can assign 1 over 6 as the probability of occurrence of each of the 6 possible outcomes. Now, if we're going to define a random variable here that will have a discrete uniform distribution, then we can just consider, say, x to be the number of dots that we can observe when we roll a fair die. So in that case, x will also have 6 possible values, 1 through 6. And therefore, the density or the probability mass function of the random variable x will be f sub x of x is equal to 1 over 6 times the indicator that x takes on the values 1, 2, up to 6. Okay, so we're now ready to derive the mean, the variance, the moment generating function of a discrete uniform distribution. Okay, but we will be deriving the case where the distribution or the random variable as the parameter capital N. In other words, it has n possible outcomes. Okay, so for the mean, we have the expected value of x is just the sum of x times its mass function, f sub x of x for all possible mass points x. So for the discrete uniform case, we will get the sum from 1 to capital N of x times the uniform probability, which is 1 over capital N. So we can just factor out from the sum 1 over n. And expanding the sum, we will have 1 plus 2 plus 3 plus n. So that means we just have to sum up the n possible outcomes. Okay, now in reality or in practice, the outcomes might not be consecutive positive integers. But for the case of deriving the mean, let's just say that the outcomes are consecutive and positive integers, so that the sum will just be capital N times n plus 1 all over 2. And since we have 1 over n here, we can just cancel n, and so we get capital N plus 1 all over 2. That's the mean of a discrete uniform distribution. Okay, for the variance, we're going to use this formula. We have already discussed in our previous discussion that the variance of a random variable x is just equal to the expected value of the square of the random variable minus the square of the mean of the random variable, or var of x is equal to ex squared minus e of x squared. Now, we know already from above what is e of x, so that's n plus 1 all over 2. So we need here to get the expected value of x squared, and that will be the sum of x squared times 1 over n from 1 to positive n. We can factor out 1 over n, and then the sum will be 1 squared plus 2 squared plus 3 squared, etc., plus capital N squared. So this is the sum of squares of consecutive positive integers. Now you can Google the formula for this, but the formula for that sum is, or the general form for this sum is 2n plus 1 times n plus 1 all over 6. So you can cancel this n, and we are left with what? I will multiply this. We will have 2n squared plus 3n plus 1 all over 6. Okay, so we substitute that to the variance formula. We will have var of x is equal to 2n squared plus 3n plus 1 all over 6 minus the square of the mean. So we have n plus 1 squared all over 4. So simplify that, we will get this expression right here, and so we will get the variance of x is capital N squared minus 1 all over 12. Okay. Now for the moment generating function, we have by definition m sub x of t is equal to the expected value of e to the tx. So since x is discrete, we can compute the expected value as the sum of e to the tx times f sub x of x. So that will be the sum from 1 to capital N of e to the tx times 1 over n. So we just have to factor out 1 over n from the sum, and that's it. That's the moment generating function of a discrete uniform distribution. Okay? Next, we have the Bernoulli distribution. Okay, before we talk about this distribution, it's actually related to the Bernoulli trial. A Bernoulli trial is a trial with only 2 possible outcomes. Okay, so the possible outcomes in a Bernoulli trial are labeled success, quote-unquote success, and quote-unquote failure. And mathematically, we can represent success by 1 and failure by 0. Okay, now in the Bernoulli experiment, we denote by small p the probability of occurrence of a successful outcome. And so the probability of occurrence of a failure, quote-unquote failure outcome, will be 1 minus p, because there are only 2 possible outcomes, and we know that the sum of the probabilities of all possible outcomes in a random experiment must be equal to 1. Okay, so if we denote by x a random variable that follows a Bernoulli distribution, then its probability mass function is given by this one. So f sub x of x comma p. So p here is the parameter. That's the probability of success. Then it will be equal to p to the x times 1 minus p to the 1 minus x times the indicator that x takes on either 0 or 1. Okay, now if we're going to substitute 1 here, we must be able to get the number p, because that's the 1 here corresponds to the quote-unquote success outcome. And we say that, we just said that the probability of occurrence of a success is equal to p. So we must be able to get p here when we substitute 1, which is true, because 1 minus p raised to 1 minus 1 is just 1. And p to the 1 is p. And also, when x is 0, we will get the probability of occurrence of a failure outcome. So p to the 0 will be 1, 1 minus p raised to 1 minus 0 will be 1 minus p. Since there are only two possible values the Bernoulli random variable have, then we can easily compute its expected value and its variance. So for the expectation, we have the sum of x times its corresponding probability mass function. So when x is 0, we will have 0 times, we substitute 0 here, so we get p to the 0 times 1 minus p raised to 1 minus 0 plus 1 times the probability when x is 1, we substitute 1 here. That's why we get p to the 1 times 1 minus p raised to 1 minus 1, and we will get what? P. Okay. Anyway, I've already written it here. Let's just erase that. Next, we have for the variance, we need the expected value of x squared, which is given right here. Okay, so it's the sum of x squared times the corresponding probability. So when x is 0, we'll have 0 squared times that probability, which is just 0 anyway, since we have here 0 squared, and 1 squared plus 1 squared times p to the 1 times 1 minus p to the 1 minus 1, and that is also equal to p. Therefore, the variance will be p minus the expected value of x squared, or p squared, and therefore that is just equal to p times 1 minus p. Now here, we will be using q for the expression, or for the number 1 minus p. Now for the moment generating function, we have the sum from the sum of e to the tx times its corresponding probability. So when x is 0, we'll have e to the 0 times p to the 0 times 1 minus p to the 1 minus 0 plus e to the t, that's when x is already 1, times p to the 1 times 1 minus p to the 1 minus 1, and that will be 1 minus p plus p times e to the t. So that's the moment generating function of a Bernoulli distribution. Okay? So I hope that that was clear. Okay. Now, let's proceed to the binomial distribution, which is related to the Bernoulli distribution. Okay, so it's like we start off with a binomial experiment. A binomial experiment is an experiment where we repeat a Bernoulli trial or a Bernoulli experiment n times. Okay, and then in each of the trial, the probability of occurrence of the quote-unquote successful outcome should be constant. So it should remain constant. And the trials, or all trials, must be mutually independent. Okay, so just like before, we will denote by small p the probability that we observe a success or a successful outcome. Okay, now the random variable here that follows the binomial distribution, if we're going to denote that by x, is defined to be the random variable that counts the number of successes. out of the n repetition of the Bernoulli trial, so that the possible values of x will be 0. And that is the case when in n repetition, all outcomes of the experiment are quote-unquote failures. Or we can have one possible or one successful experiment or two successful experiments, etc., etc. Or if we got lucky, all n experiments will result to success. Thus, the possible values of a binomial random variable x are 0, 1, 2, up to the number n, where n is the number of times that we repeat a Bernoulli trial independently. Okay, so the density of the binomial distribution is given by f sub x, which is a function of x and two parameters n and p. P here is the probability of success in every Bernoulli trial, and n is the number of times that we repeat the Bernoulli trial. And the density is given by n taken x times p to the power x times 1 minus p raised to n minus x. Again, this 1 minus p may be denoted by q times the indicator that x takes on the values 0, 1 up to n. Okay, so let us now derive the mean, the variance, and the moment generating function of the binomial distribution. Anyway, I have already written here that the expected value of x is np, the variance of x is np times 1 minus p or npq, and the moment generating function is p et plus q raised to the n power. If you notice, PET plus Q is just the moment generating function of the Bernoulli distribution. Let me just write this into PET plus Q. Now, in the binomial distribution, the moment generating function is just the moment generating function of the Bernoulli distribution raised to n, where n is the number of times that we repeat the Bernoulli trial. So we start with the mean. Okay, so the expected value of x is the sum from 0 to n of x times its density, which is n taken x, p to the x times q to the n minus x. Okay, now if we're going to expand the sum, the first term will just be 0. So we can actually rewrite the sum as, we can change the index from 1 to n, since the first term is 0 anyway. Okay, so we have the sum from 1 to n of x times n taken x times p to the x times q to the n minus x. Now, we will try to simplify this expression, x times n taken x. If you can recall, the binomial coefficient n taken x is given by n factorial, this one, n factorial over all over x factorial times n minus x factorial. Now, take note, the definition of n factorial is equal to n times n minus 1 times n minus 2 times etc. etc. times 3 times 2 times 1. So it's we just compute the product of n consecutive positive integers. That's n factorial. But we can rewrite that actually into n times n minus 1 factorial, or n times n minus 1 times n minus 2 factorial. So we will use this idea here to simplify x times n taken x. So for this x factorial, in the denominator, we write that into x times x minus 1 factorial, so that we can divide x. We can just divide that x because we know that x is non-zero. Okay? So we get n factorial over x minus 1 factorial times n minus x factorial. But we will also factor 1n here. So we write that into n times n minus 1 factorial. And this expression right here is just equal to n minus 1 taken x minus 1. Okay, so that the sum becomes the sum from 1 to n of n times n minus 1 factorial all over x minus 1 factorial times n minus x factorial times p to the x times q to the n minus x. I'm going to factor out this n from the sum and 1 power of p, so that we will have the sum from n times p times the sum from 1 to n, x equals n, of we knew already that this one is n minus 1 taken x minus 1. So we have p to the x minus 1 now because we factor out 1 power of p times q to the n minus x. Now we change some variable here. We let m be equal to this number, n minus 1, which would imply n is equal to m plus 1. Okay, with this introduction of new variable and y equals x minus 1, we will have to also change the limit of the sum with respect to y and m. Okay, here, when the variable is x, the limit starts from 1 and ends at n. So when we introduce y equals x minus 1, when x is equal to 1, the value of y will be 0. And when x is equal to n, the value of y will be n minus 1, which we denote by m. That's why we have the sum from 0 to m. And n minus 1 is now m, x minus 1 is y. The power of p now is y, and the power of q will be m minus y, because n minus x is just equal to m plus 1 minus y plus 1, or m minus y. Okay, so what is this? From the binomial theorem. Okay, recall the binomial expansion. A plus b raised to the power n can be written as the sum from 0 to n of n taken x times a to the x times b to the n minus x. Now, this is similar to this expression. P is our a, q will be our b. So this sum is actually just p plus q raised to the power m. But p plus q is equal to 1. So 1 to the power m is just 1. Therefore, this is equal to n times p. Okay? So that's the mean. For the variance, okay, we are used to using the expected value of x squared. But for the binomial distribution, we will be using the expected value of x times x minus 1. Now, if we're going to distribute x here, we will have the expected value of x squared minus x. And since the expectation operator is linear, this expectation is equal to ex squared minus ex. Okay, now we know that the variance is the expected value of x squared minus the square of the expected value of x. Okay, so if you're going to use this expression in deriving the variance, then we will have the variance of x is equal to the expected value of x times x minus 1 plus the expected value of x minus the square of the expected value of x. However, I'm going to give as an exercise to you guys the expected value of x times x minus 1. Okay, so you use the same technique that we did in finding the expected value of x. Okay, so you must be able to get the variance of x, which is npq. So let's now proceed to deriving the moment generating function of the binomial distribution. As discussed, it is denoted by m sub x of t, or the expected value of e to the tx. So we get the sum from 0 to n of e to the tx times the density n taken x times p to the power x times q raised to n minus x. Now we have here e to the tx and p to the x, and we can combine them actually. E to the tx can be written as e to the t quantity raised to the power x times p to the x. Okay, so using the laws of exponent, we can simply write this one as p times e to the t quantity raised to the power x. That's why we have here the sum from 0 to n of n taken x times p et raised to x times q raised to n minus x. And again, this is similar to the binomial expansion formula. So this is just equal to the expansion of PET plus Q raised to the nth power. So that's the moment generating function of the binomial distribution. Okay. So we have here an example. Consider the experiment of throwing a fair die 10 times. Okay, let x count the number of times that we observe a number of dots greater than 2. Find the probability that x is equal to 2 and the probability that x is equal to 8. Now, you might wonder why our experiment here is throwing a fair die. We know that there are 6 possible outcomes, but we can actually dichotomize the outcomes of the experiment. Okay, so our success here will be observing a dot that will be greater than the number 2. So when we observe 3 dots, 4 dots, 5 dots, or 6 dots, that will be considered success. Observing a 1 or a 2 will be considered a failure. Therefore, the probability here of observing success will be 4 out of 6 because there are 4 dots that are greater than 2. And since the die is fair, each outcome has equal chance of occurrence, so that will be 1 over 6. And the probability of observing a failure will be 2 out of 6 or 1/3. So the probability that x is equal to 2. So if we repeat the experiment 10 times, and if we're going to count the number of times that we observe a successful outcome, then our random variable x follows the binomial distribution. So the probability that x equals 2 is 10 taken 2 times 2/3, that's p, raised to the power 2 times 1/3 raised to the power 8. Okay, so you can just compute this value using your calculator or any software, computer software, while the probability that x is equal to 8 is equal to 10 taken 8 times 2/3 to the power 8 times 1/3 to the power 2. Again, I leave to you to compute the value of these two expressions, two numbers rather. Okay, so that's it for the binomial distribution. Now let's skip first this hypergeometric distribution and the Poisson. Let's proceed to the geometric distribution, because this one is related to the binomial distribution and the Bernoulli distribution. We have the geometric distribution. Okay, so for this distribution, let us consider first an experiment. Okay, the experiment is like this. We're going to perform repeatedly a Bernoulli experiment or a Bernoulli trial. Okay, so we're going to perform it repeatedly, and we are going to stop the experiment if we can observe the first success. Okay, again, our experiment is to repeatedly perform a Bernoulli trial or a Bernoulli experiment independently, so that the probability of occurrence in every trial will be the same or is a constant, and then we're going to stop the experiment once we have observed the first success. Okay, now from that experiment, we define a random variable x to be the number of trials required until the first success. For example, if we have if we observe the first success in the fourth trial, then the value of the random variable x is 3. Okay, because we say that the random variable is the number of trials until the first success. So if the first success occurs on the fourth trial, the value of the random variable x will be 3. Another example, if the first success occurs on the 10th trial, then the value of the random variable x is 9. Okay, that's our experiment. Now, the random variable x that we have just defined follows the geometric distribution. Okay, now from the way we set up the experiment, what are the possible values of the random variable x? Let me just write the experiment here. We repeatedly perform a Bernoulli trial. Which are independent. With probability P of success. And then we define x as the number of trials until the first success. Okay. So the possible values of x. The possible values of x will be 0. That's the case when we observe a successful outcome on the first trial. Therefore, we have not observed any experiment prior to the first success. X is 1 when we observe the first successful trial on the second try. Or x is equal to 2 or 3 or 4, etc., etc. Okay, so x can take on an infinite value, non-negative, okay, non-negative positive integers. Okay, so what is now the probability density function or probability mass function of x? The probability mass function of x depends on the parameter p, where p here is the probability of success, of observing a successful outcome. Okay, now, since x is the number of trials until the first success, okay, so we have only observed one successful experiment. Okay, but we have observed how many failure experiments? That's the random variable x. So the density of x will be p times 1 minus p raised to x. 1 minus p is raised to x because that's x is the number of times that the failure outcomes occurred. So it should be raised to the power x, so that the total number of outcomes is x plus 1. Okay, x for the total number of failures and 1 the only successful outcome. So the density function or the density mass function of a geometric random variable is given by p times 1 minus p to the x times the indicator that x takes on the values 0, 1, 2, etc., etc. There. That's the probability mass function of a geometric distribution. Now, what is its mean? What is the expected value of x? To derive that, we need this result in algebra. The sum of x to the r from 0 to infinity is equal to 1 over 1 minus x for all x whose absolute value is less than 1. And of course, yeah, that's it. That means x is a number whose absolute value is less than 1. So it could be 0.5, negative 0.5, 1/2, negative 1/2, 3/4, negative 3/4, etc., etc. So we will be using this result. This is the geometric series. Okay, so the geometric series is only convergent when the absolute value of x is strictly less than 1. Okay, so now the expected value of x will be the sum. We know that x takes on the values from 0 to positive infinity, so the sum will be from 0 to infinity of x times p times 1 minus p raised to the power x. Okay, we can factor out p because it's independent of x, so we have p times the sum from 0 to infinity of x times 1 minus p raised to the power x. Okay, so we have quite a problem here since this expression is not quite similar to this. Although if we're going to get rid of x, then we will have an expression similar to x to some power. Okay, now, since here, in our result here, if this is a convergent sum, then we can actually apply some operations here, such as differentiation or integration. So in the case when we apply differentiation here, we'll have for example, the derivative with respect to x of the sum can just be written as the sum from 0 to infinity of, we can write here inside the sum the operator d dx. Since we can do that since the series is convergent. We cannot do that if the series is not convergent. So since the operator is now inside the sum, we simply get the derivative of x to the power r with respect to x, and that will be r times x to the r minus 1. Okay, so we need an expression which is similar to this one. Okay, but this is already close to this expression. Therefore, what we're going to do here is I'm going to factor 1 power of 1 minus p out of the sum. So I'm going to have to write p times 1 minus p, so that my sum will be from 0 to infinity of x times 1 minus p raised to x minus 1. Okay. Now, what is that expression? X times 1 minus p times x minus 1. Consider this one. If we're going to get the derivative with respect to x of 1 minus p raised to x, then this is equal to x. Sorry, it's not with respect to x. It should be with respect to p, because that's our unknown here. So with respect to p, that will just be power rule. So x times 1 minus p raised to x minus 1 times the derivative of the base is negative 1. Therefore, the negative of the derivative with respect to p of 1 minus p raised to the power x is equal to x times 1 minus p to the x minus 1. Okay, therefore, we can write this as p times 1 minus p times the sum from 0 to infinity of the negative of the derivative with respect to p of 1 minus p raised to the power x. Again, this is a convergent sum since our p here is a number from 0 to 1, so its absolute value is less than 1. We can just actually factor out the differential operator, so we will have the negative of p times 1 minus p times the derivative with respect to p of the sum from 0 to infinity of 1 minus p raised to the power x. This time, we can now use this result here to get this sum. So we have negative p times 1 minus p times the derivative with respect to p of what is now our sum here. That sum will be 1 over 1 minus 1 minus p. Okay, so I hope we're doing it right. So we have negative p times 1 minus p Okay, so what's the derivative of 1 over p? 1 over p is just equal to p to the negative 1. So thus, the derivative with respect to p of p to the negative 1 is equal to negative 1 times p to the negative 2, or negative 1 over p squared. So we get negative p, 1 minus p, times negative 1 over p squared, and we get 1 minus p over p. That's the mean. Okay, 4. That's right here. The expected value of x is equal to 1 minus p over p, or q over p. That's the expected value of a geometric distribution. Okay. Okay, again, for the variance of x, we will be using the expected value of x times x minus 1 plus the expected value of x minus the expected value of x squared. Okay, so again, I'm going to leave as an exercise the expected value of x times x minus 1. And let me just write that into the sum from 0 to infinity of x times x minus 1 times p to the x times 1 minus p to the sorry, it's not p to the x, it's p. It's x. This will be an assignment. Okay, now for the moment generating function. Expected value of e to the tx is equal to the sum from 0 to infinity of e to the tx times p times 1 minus p to the x. Okay, can we get the sum of this? This is equal to p times the sum from 0 to infinity of, we can combine e to the tx and 1 minus p to the x, so that will be, anyway, let me just write that into e to the tx. I'm gonna use now q to the x. So this is just p times the sum from 0 to infinity of q times e to the t quantity raised to the power x. So provided that q times e to the t is a number between whose absolute value is less than 1, then we can write the sum as p times 1 over 1 minus q e t, or p over 1 minus q e t. Again, q e t should be less than 1. So that's the moment generating function of a geometric distribution. Okay, so you have how many assignments already? This one. And the variance of the no, not that one. Anyway, I'm going to post in MS Teams your assignment, guys. So I guess that's all for this video. We still have some distributions left, but we will do that in the next video.